So I want to go over a projectile motion in two-dimension problem that's a little more challenging. I want to go over a problem where the height at which the projectile is launched is different from the height at which it lands. And that makes it a little more tricky. So this is the challenge problem from this unit that I want to go over. So just to go over this solution, we have a missile being launched, and it's being launched from 50 meters above its landing point. And it's being launched at an angle, so this is an angle launch problem. The velocity to which it's being launched is 75 meters per second, and that's at 25 degrees. That's the launch angle. Anytime we have an angle launch, we can find the x and y components to the velocity. So I'm going to resolve this into its x and y components. I'm going to use cosine 25 degrees equals Vx over 75.0 meters per second. And so Vx will equal, make sure your calculator's on degrees, 68.0 meters per second. So I'm just going to write that in on my little diagram here. Then I'm going to find the vertical component of my velocity using sine and Vy. The y component should be 31.7 meters per second. So I'm just going to write that in. Now the reason I did that is one of the key ideas we're playing around with here in these projectile motion problems is we can work with one dimension independent of the other one if we want to. So I'm going to look at what's happening horizontally independent of what's happening vertically. And so I'm just going to sort out all of the vertical and horizontal information that I have. Horizontally, I know the velocity in the x direction is 68.0 meters per second. I'm trying to find the horizontal distance that the object travels. And the other thing I know about the horizontal stuff is there's no net force acting in a back and forth or horizontal direction. So it means the object is moving at a constant velocity. So I'm going to be using the equation v equals d over t to solve the horizontal stuff. So if I'm trying to find d, d is going to equal v times t. So I need to know two things to find my answer, the velocity horizontally and the time that the missile's in the air and has to travel horizontally. So I want to use the vertical stuff to find t because as it's traveling horizontally, it's also traveling the same amount of time vertically. So what do I have vertically? Well, I have an initial velocity. It's 31.7 meters per second, the initial velocity upwards. The acceleration rate on the moon, negative 1.70 meters per second squared. The displacement of this missile through the course of its trip is negative 50 meters. And I'm going to try to find the time that it travels vertically. So if I think back to my equations, the one that I would be led to is d equals vi t plus 1/2 at squared. And normally that would work quite nicely, except in this particular instance, the initial velocity of the rocket isn't zero, so I can't cancel out the first term. So I have t in two of the terms, and factoring it gets a little bit messy. You can use the equation for factoring quadratic equations, but we're not going to go there. What we're going to do in this course is we're going to find something that's not even asked of us in the problem. The final velocity vertically, the instant before this missile hits the ground. So what I'm going to use for an equation is Vf squared equals Vi squared plus 2AD. And so the initial velocity vertically was 31.7. I'm not going to put the units in just because it's going to save me some space. Then 2 times the acceleration rate, which is negative 1.70. And then the displacement, negative 50.0 meters. So when I punch that all out, I come up with 1174.9 meters squared per second squared. And so I take the square root of both sides. So VF is going to equal plus or minus 34.3 meters per second. I'm going to choose the minus because the rocket or the missile is going to be traveling downwards the instant before it hits the ground. So once I know the final velocity, I'm going to use the equation A equals VF minus VI over T to find the time that it's in the air for. So I just did this in 2 steps instead of 1. The final velocity, negative 34.3 meters per second, minus the initial velocity, 31.7 meters per second, all over the acceleration, negative 1.70 meters per second squared. So the time comes out to be 38.8 seconds. And now that I know the time, I can go back to my d equals v times t equation. So my velocity, 68.0 meters per second, times my time, 38.8 seconds, and I get my displacement, which is 2.6 times 10 to the 3 meters, which is the same as 2.6 kilometers. And that would be my correct answer to 2 significant digits.